All right, so I'm going to speak today about data-driven science and climate-biosphere interactions in the work of my laboratory. And in general, my department and my group were interested in how the atmosphere, lands, and oceans interact as a system and how they're changing over the span of human lifetime. And so in my laboratory, we use satellite remote sensing observations, atmospheric measurements, and Earth system models to study these interactions. And we focus actually on terrestrial ecosystems and how they respond to climate change and how they're interacting and feeding back to accelerate or decelerate climate change in different regions. And so climate change and global warming are several of the most outstanding environmental challenges of this century. And in the context of adapting to climate change, it's important that we amplify our ability to develop early warning systems for drought stress and fire risk, as we expect in the future the nature and the number and the duration of extreme events to change with warming. So this is a diagram showing the interactions between fire and the climate system. So there are many aspects of climate that influence fire dynamics, including rainfall, winds, temperatures, length of the fire season, ecosystem composition, and human behavior that controls ignition or suppression. And then in turn, fires at a regional scale will modify carbon dioxide, methane, greenhouse gases, aerosols that influence air quality, human health, but also change the radiation budget, the surface reflectance, ozone, and the amount of water that's evaporated off the surface. So today I'm going to provide an example of how we can use different satellite data sets to develop early warning systems for fire risk. And so these are some of the data that we use in my laboratory, studying on different continents. So one data set that's really nice now that is from NASA. It's the Terra and Aqua time series of global imaging of the land surface and of atmospheric composition. We also use data from Landsat, from NASA's tropical rain monitoring mission, the upper right-hand satellite that provides rainfall data globally, a series of satellites that provide information about sea surface temperatures and how they're changing, and then GRACE in the lower right-hand corner actually measures directly gravity anomalies and soil moisture variations. So a project that we started recently, as one example, is to try to predict seasonal fire risk in the Amazon basin. So the Amazon is a biodiversity hotspot. It stores a great deal of carbon. The carbon in these forests is vulnerable to drought and to fire. So when a fire escapes from someone's farm, if it escapes during a drought event, it will keep burning through intact forests and it'll kill the trees, and that carbon is released into the atmosphere. Roughly about the same number of fires and farms are starting fires every year, but the duration and the extent of the fires is modulated considerably by climate. And so, as you can see here in the lower right-hand panel, there's a time series of how the fires in the Amazon vary from one year to the next. So they can vary by over a factor of 2. And during 2007, 2005, and 2010, those were extreme, once-in-a-century type droughts in the Amazon that occurred in a cluster that have really triggered a lot of mortality and fire across the region. And so when we were starting on this problem, we just wanted to understand how climate modes that are represented by sea surface temperatures, how they influence fires in the region. So we looked at the relationship on the left between the Pacific, and that area is called the area that we looked at is called the ONI, or the El Nino Index, which is in the middle of the tropical Pacific. It's a measure of the sea surface temperatures. And the Atlantic, we looked at different regions, including the Atlantic Multi-Decadal Oscillation Index, which is shown there with its variations. And what we learned when we looked at the relationship between fires in these forcing areas is that the pattern from El Nino on the upper left-hand panel influenced fires in a different part of the Amazon than the places that the North Atlantic modified the fires from one year to the next. And what really surprised us is that if we did a phase analysis, that it was actually the sea surface temperatures that were 6 or 8 months in advance that modified the length and severity of the fire season. So this led us to think about, could we develop a predictive system? And so we developed some simple regression models, shown on the top equation, combining information from the Atlantic and the Pacific to try to explain variability in fires across the Amazon. And you can see in the lower right-hand panel, that's how well our model does using some of this MODIS imagery. And so there's a big cluster in the middle, a very highly vulnerable area of the Amazon that is potentially predictable when you combine information from the Atlantic and the Pacific. And so mechanistically, we think what's going on and allows this predictive system is that during the wet season, from like December through March, the amount of soil water is set by the amount of rainfall. And so even though there are no fires during the wet season, if the soils are not fully recharged, and this is the time that it's connected, you have these teleconnections between the sea surface temperatures and the climate and the fires. So during the wet season, the sea surface temperatures modulate the precipitation in the Amazon, and then coming into the dry season, April, May, and June, in a year where there's not enough sufficient recharge of the soils, then there'll be less water to evaporate in the atmosphere, cool the surface, and keep the humidity levels high. And so in those years, the fires spread. So we think there's a mechanism behind this relationship, and so we're able to predict with a moderate accuracy the distribution of fires during the left-hand panel are low fire years. MODIS is the data, and our model is shown with the predicted, and then also high fire years. So there's a lot of variability. It depends on the state of what's shown in the middle. It's the state of the Pacific or the Atlantic. And we used our data from the early part of the MODIS record. We tested it with 2010. We were able to capture some of the spatial variability in fires. And then we also tested it with a lot of data before the MODIS era from other satellites. And so we then actually released early fire risk forecasts to help with conservation in the Amazon. We did this in 2011 and 2012, and it was great. It worked well. But then in 2013, our forecast actually failed. And it was the same year that the hurricane forecasts failed from NOAA. And so what I've got plotted on the right-hand panel in the bottom is the relationship between hurricanes and fires. Maybe it's not quite as spurious as the relationship between Kentucky marriages and chickens or whatever Park showed earlier. But we think there is actually a mechanistic link between the hurricanes. You can see the black is the hurricanes and the red are the fires. There's a very strong correlation. And the reason we think both our fire system failed and the hurricanes failed is that the North Atlantic flipped in its state and warmed faster than we expected. So future directions, these are directions I'd like to collaborate with faculty and students on, is that we'd like to learn, if you look at this as a map, this is how the world rainfall is going to change at 2100 according to the latest Intergovernmental Panel on Climate Change scenario for business as usual. You can see that the Amazon is getting drier. There's actually a lot of disagreement among the models. And so we'd like to do an analysis where we try to figure out what are the mechanisms that describe the model-to-model variation. Why do some models predict a lot of drying in the Amazon and some not so much? We'd also like to extend our analysis from the Amazon to look at where there are hotspots around the world that we can that are predictable, where we can develop early warning fire systems. And then finally, we'd like to further explore how do we use sea surface temperature data optimally and soil moisture data to develop fire risk models. So right now we're using these block indices, and we think that there's ways to harvest the sea surface temperature data more effectively. So thank you.